Welcome back to CSC 31 and lecture 20. So this is the second part of our CPU lecture 20. So in the last part, we talked about how we build our choo-choo train track from small 5 stages data path to now semi-complete data path. Okay. So far with this data path, we can pretty much take care of most of our I format and R format instruction. Okay. So we still have J format, haven't covered yet. So we'll talk more about that later in the lecture, maybe in the next lecture. So, and actually before we go into more about this data path, I would like to switch gear to talk about some concept of digital logic, because this will give us a better idea of how to do the control. Okay, so in the hardware CPU, there are 2 types of circuits. Okay, and the first one is what we call combinational logic circuit, or CL circuit. So basically, it is a circuit unit that perform action. Okay, so for example, an adder. Okay, so how do you add 2 numbers together? Right? So this is a type of combinational logic unit. Okay. And the other type is called state element. So pretty much what it does is to store information. So for example, a register is an example. Okay. So within the CPU, we talk about the CPU will go through 5 stages. Right? So basically, if you think about it, each stage is a compound of combinational logic circuit and a state element. So what happened is that every single stage, you have a black box to do the job of that stage. And by the end of this stage, the result of that black box will be stored in a state element or a register. Until the next clock come out, okay, we will use this result and go to the next stage. Okay, and then, so basically this is the idea of synchronized system. So when the clock comes in or goes up, you perform one action. By the time the clock ends, you store the result. Okay, and then when the clock goes up again, you use this result to do something else. And then by the clock ends, you store the result. Okay, so this is how you create synchronization. Okay. Yeah, so I'm not going to talk too much about the detail about this synchronization, and because this is more in the advanced level. Okay. All right, so state element is very simple. Just think about a register as your camera. Okay, so you have a viewfinder, keep looking at different objects, right? Point of interest, right? So your portrait, your selfie, whatever, right? But it doesn't mean that you will save the image, right? Right away, right? You have to tap on the shut button, right? Or you have to click the button. You have to press the shutter, right? So basically, the load means the shutter, right? So if you enable it, now your camera will take a snapshot of whatever it is and then output it to the screen. Okay, so this is what we call a register. So basically, inside the CPU, the 5 stages, the clock is the one who controls the snapshot. So whenever the clock goes up, it sends a signal to the register to copy whatever the register sees, take a snapshot of it, okay? And then the output will be able to use that snapshot. So it doesn't matter what this input changes now, because the output will only use the snapshot version until the next clock comes in to take another snapshot. Okay, so that's how you create the states. So in this case, you use the clock to do it. Okay. So what kind of states elements are inside our CPU? We just talked about that. Pretty much the registers. that we use, as well as the cache, as well as the main memory. But cache is a lot faster. Okay, so those are the most expensive memory you can get. Okay, so it helps control the flow. So we'll talk more about these features in CSC 140. So don't worry about that. Okay. So what I want to focus on for the rest of the lecture here is how we create the actual action, right? So when we have 4 input, there will be 1 output, right? So what is the circuit behind it? So this is what we call combinational logic circuit. Okay, so how can we design this circuit so that it can perform what we want? Okay? So to do that, we need to, first of all, create a truth table. So based on the combination of these 4 input, I will generate an output, right? So based on the combination of the 4 possible input, so you can see that, right? Since I have 4 input, I will have 2 to the power of 4, which is 16 number of output of the function unit of y, right? So you can have different combination of y. Okay? And of course, y is just a bit, right? So which means that y can be repeated based on these 4 input. So this is what we call combinational logic or digital logic. Okay, so for example, this is an example of exclusive OR. What is an exclusive OR? So when you go to a high-end restaurant, and you order a meal, it will come with soup or salad. Okay, so since this is high-end, they won't allow you to have both unless you pay extra. Okay? So this is exclusive OR. It's soup or salad, but not both. Okay, so that's why when you have both, you have a 0. You are not allowed to do that. So soup or salad. So since I have 2 bits as input, okay, so I will have 4 possible combination, and then I have 4 possible output. Okay, so when both bits are 0, y is 0. When both bits are 1, I have y is 0. So, or I can have a 2-bit adder. Okay, so here I can see that you can see that I have A, which is 2 bits. So again, I have a stroke with 2, so which means that I have 2 bits coming in. B is also 2 bits coming out. So now, how many bits will be output? At most 3 bits, right? So what is the maximum of for 2 bits? 3, right? 1, 1. So I have 3 plus 3, output will be 6, which is 0, 1, will be 1, 1, 0. So you only need 3 bits to record 2 bits, the sum of 2 bits. Okay, so you can see with 2 bits, I have how many rows? How many rows are there? 2 to the 4, right? Because totally I have 4 bits. So I have 2 to the 4 number of combination. And of course, some of them are repeated, but still, the truth table is long. But now, how many bits are in a register? 32 bits, right? So now when I add 2 registers together, how many rows of truth table do I have? Humongous. So I have 2 to the power of 32, which is impossible to use a truth table to design the logic. So that's why with add, we don't do that, okay? Because it's just too much to handle. Okay? So adder is actually a lot easier. You can do just single bit to bit addition without using a truth table. Okay. All right. So the other example, majority. What does that mean? When I have more than 2 or equals to 2 or at least 2 ones, then you have a true. So this is called majority, right? So here, no ones, false. No, only 1, 1, false. Only 1, 1, false. 2 ones, true. 1, 1, false. 2 ones, true. 2 ones, true. 3 ones, even better, true. Okay, so this is the majority logic. So now, based on the logic, okay, so we have something like this, right? The truth table. We want to be able to create a circuit so that I can create a combinational logic. So why is it called combinational? It's because the basic units are all this basic logic, and or not. Okay, so when you say not, usually you put a triangle with a circle, but sometimes you just put a circle. That would be a not. Okay, and is what? The regular and operator, right? When both are ones, then you have a one. Or is when at least one is one. Okay? Not means the opposite. Okay? So on top of these three, you can also have nor, nan, and exclusive or. So exclusive or is a little bit special. So basically your combinational logic, whatever the big black box is just gonna be a combination of all these 6 gates. Okay, so it's pretty amazing, right? So by pick and choose of these and combine them, you create all sorts of truth table. Okay, so in this class, I don't expect you to do a lot of difficult design because for me, when I learned this, it took me 1 semester. There's a special class for that. So that's why I don't expect you to be able to do all sorts of logic design. Okay, so don't worry about that in your exam, but I will ask you basic ones. Okay, so which means that you need to pay attention to the rest of this lecture. Okay, so here is another example. Okay, so this is the 2 input gates for exclusive OR. So I have more than 2. Okay, so how do you do exclusive OR? So this is the 3 input exclusive OR logic. So what can you see here? When there's 1 here, I have a true. There's 1 here, I have a true. When I have 2 ones, not true. 1 true. 2 ones, not true. 2 ones, not true. 3 ones, true. What behavior do you observe for the exclusive OR? When I have odd number of true, exclusive OR will be true. Think about when you have 2 inputs, same thing, right? When you have either one, you have a true. So if you have only odd number of true from the input, then the output is true. So this is exclusive OR. So now the question is, how do you connect or how do you come up with this logic, right? From this truth table, magic, right? So you draw a box here. That's your combinational logic circuit already, right? You have 3 input here, and you have a black box. It gives you the output. So the question is, giving you the truth table, how do you actually create it? I don't know whether you have taken discrete math already. If you have taken discrete math already, you know what I'm talking about. So hopefully you have taken already, because you should have taken, or you should have been taking it right now, because I expect you to take algorithm class next semester. Because don't drag too long, otherwise you won't be able to graduate on time. All right, so here I have the truth table, right? So the question is how I can come up with this logic. Right? So, but with this logic, in discrete math, we learn how to write it into the linear algebra, linear algebra, Boolean algebra form, right? I have what? This is an AND, this is an OR, right? So I have what? A and B. So I have A and B. So that means AND, right? In discrete math. And now I have a B and C. B and C here. And then I have what? A and C, which is here. So you have AB, BC, AC. The output AB, BC, AC, right? And what do you do with them? You put them into an OR operator. OR means plus, right, in Boolean algebra. So you have what? AB or BC or AC. So this is the Boolean algebra form of your Y. So you can, from a logic system gates, system of logic gates, you can write the output in terms of input. All right. So this is how we write it in Boolean algebra. So now the question is, how do we connect this information, the knowledge that we learned from this slide, to the truth table so that I can draw the system of logic from the truth table. And so in order to do that, we need to review the Boolean logic algebra. And so I'm not going to review that because you should have learned that in your discrete math class. Okay, so just remember that in the exam. I won't ask you some difficult ones, okay, to prove or something, because you have done that in your discrete math class. But I would expect you to do some basic ones. Okay? For example, to take out one, right, the associativity, right, and the distributive. So for example, here I have something like this. So I have A and B, or A or C. Okay, so now I can simplify that by taking A out, distribution, right? So when I take it out, I have B or 1. So now what is that? B or 1, no matter what B is, when you have or something with a 1, it's always 1. So you have the identity, right? And now I have A or C. So now the final answer is A or C. So why is it important? Which means that if you have this answer, you only need to draw a gate. That's all. But if you have this answer, you have to draw 1 gate, 2 gates, and 3 gates. So you lose, well, kind of you lose points if your exam is not right? But on the other hand, you waste your hardware because instead of using 3 components, I can use 1 component already. So I make my CPU smaller, right? So, but these two have this equivalent functionality, so I can test. And so in circuit design, or in digital circuit design, I should say, well, we usually use Boolean algebra to verify whether our circuit is the same. Okay, so I can simplify it so that I have a simplified circuit. So I can always use Boolean algebra to do the math to prove that, hey, my simplified form works. And actually it works better because instead of having 3 layers, I have only 1 layer. So I will have less delay because each gate has a delay. Right? So this is a lot better. So now the question is, how do I do that from truth table to gates? First of all, I need to be able to write my truth table into a Boolean expression. And this is called canonical form, or in your side box, I think it's called sum of products form. Why? Because it's multiple sum of the product, right? So this is called sum of product. How does it work? Okay, so let's see how I can do it. Let me change the screen. Okay, let me stop sharing the screen. Okay, and then start the screen again because I want to make sure I can use a pen, right? Okay, so let me start the recording. Start the screen sharing. Okay, so here, how can I write from this canonical, oops. So how do I write? I can't really draw it. But that's okay. So one way to do it is locate all the ones. Okay, here, here, here. So that's all you need. Okay. So with giving you a truth table, locate all the ones. Okay. I have these 4 rows, right? And then these 4 rows becomes the 4 products that we have. So remember that, okay? So giving you a truth table, locate the rows with y equals to 1, the output equals to 1. And then from each one, you create the product. So whenever the input is 0, you need to put a not in front of it, so that becomes 1, right? So think about it. 0, 0, 0, and I have not A, not B, not C. So what does that mean? When A is 0, what is not A? You have a 1. When B is 0 and you have not B, what is that? You have a 1, right? So let me try again. If I have A, yeah, something's wrong. Yeah, so weird. Okay. So somehow the digitizer doesn't work well. Okay, so when I have A here, so I'll just use so now when A is 0, not of 0 will be 1, right? When B is 0, not of 0 is 1. C is 0, not of 0 is 1. Okay, so that's why whenever the trick is when the input is 0, which means that you need to put a not in front of that variable. Okay, so now let's take a look at the second one. Second one, same thing, right? I have 0, 0, 1. So which means that I will have not A, not B, and now this is C is 1. So I don't need a not for C, because when C is 1, this is automatically 1. So the whole point is I want to make this block equals to 1 when I have this input. That's how you get a true, right? Same thing, the third block, I have A, not B, not C, right? And then last one, A, B, and not C. So now you have your 4 products, right? So now you use a Boolean algebra to do the simplification. So originally you have this. Now you group these 2 together. You can bring out what? Not B, not A, not B, right? Both of these 2 terms have not A and not B. Both of these 2 terms have what? A and not C. So bring them out. Not C or C becomes 1. Not B or B becomes 1. And finally, you have this answer. And you can draw out the diagram, right? You have, this is an AND, but I have a not A, not B. So I'll put a not in front of it. So I have not A, not B, and here I have one A, so there's no not here, and not C with an N. The output will be OR. Okay, or to draw it, to make it easier to draw, ignore the triangle, just put a not in front of the input and you automatically complement or take the opposite of it. Okay, so this is called canonical form. All right, so let's use this example. And unfortunately, I cannot use my pen. This is weird. I think it's because of the screen recording, screen sharing. Moment. So let's see. Let's try it again. Okay, so what do we do in the first step? Locate all the ones, right? So I have what? Oops, 2 at all. Yeah, I can draw it. Right, so no, I'm not ending it. So I have what? I have this and this, right? So let me actually open a notepad and then draw it. So probably it will be better. Okay, so let me share the screen again. Yeah, I think it's the Zoom messed up my digitizer. Okay, so what do we have? So I'm not going to draw the whole thing. So this is a lot better. Right? Okay, so I have A, B, C, D, right? And I have one row saying that I have 0, 0, 1, 1. And then I have one row saying that I have 1, 1, 0, 1. Right? So I will locate these two rows because the rest are all zeros, right? Okay, so now, okay, so I have what? D equals to, what is that? This is what? Not A, right? Because this is a 0, and this is a 0. This is a 1, so I have what? Not A, B, not B, and C. And what about this? I have what? A, B, not C. A, B, not C. And that's it. See? And then you can simplify it if you can, but if you cannot, leave your answer like this. So what do we have? So I'll have an N, right, with not A. So this is A, this is not, right? And then not B, and then with the C, I don't have that, right? So this will give you not A, not B, and C. And I'll do the same thing with, I can connect them, A, connect them, B, connect them, not C. Right? Again, with the not, you have to use a circle. And that will give you A, B, and not C. Now you combine them with an O, and that's your D. Nice. So this will be my upper D. And this becomes your combinational logic circuit. You have 3 inputs and then 1 output. All right. So this is how we do the Boolean algebra. So in this class, in your exam, I will expect you to be able to do the diagram, giving you the truth table. You are able to write it into canonical form. Okay. So the way to do it is find the rows when the output D is true. Okay. And so in this case, I have 2 rows, right? And that's it. And then just put in the input. Okay, so whenever the input is 0, you put a not to the variable. Whenever the input is true, you just copy the variable. And that's it. Okay, so that's the end of lecture 20. And review the data path as well as the canonical form in this truth table. And then in the next lecture, I'll continue with the data path and then try to wrap up in one to two lectures. Okay. All right. So I'll see you in the next lecture.